Hello, everyone. Welcome to TDWI's webinar program. Thanks for joining us today. I'm Linda Briggs. I'm an editor here at TDWI, and I'll be your moderator. Our program today is Data Architecture for IoT Communications and Analytics. Our sponsor is Hortonworks. And for our presentations today, we're first going to hear from David Lotion, who is President of Knowledge Integrity. And after David speaks, we have a presentation from Dinesh Chandrasekhar, with Hortonworks. Before I turn things over to David to get us started, just a couple background items for the audience. Today's webinar will be about an hour long. At the end of the presentations, the speakers are going to host a question and answer period. So if at any time during either presentation you have a question you'd like to submit, just type it in there on your console and send it over. Again, we'll get to as many of those as we can toward the end of the webinar. If you have any technical issues during the webinar, there's a help area below your slide window. You can click on that. If you're a Twitter user and you'd like to discuss this webinar on Twitter with fellow attendees, just include the hashtag TDWI in your tweets. Finally, if you'd like a copy of today's presentation, there's a click here for a PDF line there on your console, so you can download a PDF immediately and follow along. In addition, as always, we're recording today's event, and we'll be emailing each of you a link to that archived version so you can view the presentation again later, or please feel free to share that link with colleagues who might have not been able to make it today. Okay, once again, our presentation is Data Architecture for IoT Communications and Analytics. Our first speaker today is David Lotion, who is President of Knowledge Integrity, a consulting company focusing on information management solutions for information quality, business intelligence, and metadata management. David is a recognized expert in information management and writes and speaks on the topic frequently, including at TDWI conferences and events. So David, great to have you here. Let me get out of the way, turn the stage over to you.
Thanks, Linda, and thanks to TDWI and to Hortonworks for inviting me to talk about this. This is a topic that believe it or not, I've been thinking about and reading about practically 15 years ago, although in different forms of conception. Back then, there were talks about other types of methods of creating active networks and environments where data is being produced at the edges of these broad and deep networks that those data streams were being fed to across that network to help with building analytical models that could help in decision processes embedded across those models. So what has become known today as Internet of Things, I popped this slide up to talk about the breadth of variety of what we talk about in terms of things. That if you look at each one of these images, there's a lot of, some of them have certain things in common with each other. You know, a refrigerator, a stove, a television. There's some aspects of a power or an energy utility network, an electricity meter, or a windmill. But if you look at each one of them, or all of them together, the question is, you know, what do they all have in common? One of the things that they are increasingly having in common is that they are peppered with numerous sensors and devices and actuators that are either continuously collecting information, continuously generating information, continuously communicating information, or continuously in return absorbing information. So intelligent parking meters are collecting information about whether there's a car parked in front of them, how long that car has been parked there, what's the traffic like going on nearby, et cetera. You've got smart cities, you've got transportation networks, buses, trucks, railroad trains, airplanes, et cetera, continuously generating loads and loads of information. Even if you look in the lower right-hand corner, we've got a vending machine, and there's this conceptual network of vending machines that keep track of their inventory and what's being bought at what times of the days, and for whether it's being used, whether change is being used, dollar bills are being used, or whether credit cards are being used to make the purchases, et cetera, it can be smart enough to be able to determine to anticipate what the demand is going to be for particular types of items that are in the vending machine at particular times of the day, at particular times of the week, particular times of the year, et cetera, and be able to advance order its own replacements. And instead of having to have people walk around and actually look at what's in there and decide, what they want to put into that machine. So the ability to look at the collection of information associated with these different machines or environments and all the different aspects of what's going on within those environments gives us the opportunity to improve the ability to make contextual decision making to optimize the business processes around which these devices or things are being used. So that leads to this question of what is it really when we talk about the Internet of Things? Here's a little graphic that kind of looks at it in terms of it being a network that is connected to maybe some kind of cloud computing system. It's just an example, but the idea here is simplified a little bit in that we're looking at all sorts of different types of endpoints. We've got machinery. So if you look on the left side, we've got a printer, or we've got a computer, or we've got little devices. If you look in the lower left-hand corner, we've got maybe a disk drive, or maybe you've got a circuit board that's connected into a machine somewhere. In the upper left side of this slide, you've got applications or apps that are running on people's mobile devices, Facebook or Twitter or some of the other social media applications. Those are also continuously collecting information from the users and broadcasting a lot of that information as well. So if you look at Twitter, Twitter's a good example where information is constantly being generated and being produced and being broadcast. All you need to do is listen to those streams to be able to make use of that information. Now, the breadth of the types of devices that are out there is pretty astounding. You've got, again, transportation networks. You've got automobiles. Increasingly, if you think about the concept of driverless cars you've got a number of different devices and sensors that are embedded within automobiles already, but to be able to use the information that's being generated by those internal sensors as well as you might say, the information from the context around which a car is driving. So other cars that are nearby on the highway, or information about the current traffic conditions that are being broadcast through some kind of traffic network, or weather conditions that are being broadcast, be able to feed into the different types of processing to be able to help anticipate dangerous situations and be able to avoid getting into an accident. So this whole idea about the Internet of Things, it's not just a network. It's you might even think of it more like a web of networks at different levels of hierarchy where you're able to be streaming information in either direction, either from the device to some network of computational environments where the information is being collected and analyzed, and then analytical models that are filtering and responding to the information streams at those different points within that network and be able to influence the activities that are being done at each one of these devices. So be able to push information back to a device that says, lower the temperature because there's a danger of something catching fire. It's on a factory line. We're going to get back to an example like that a little bit later. But that's the idea of what the Internet of Things is. It's really a collection of hierarchical networks that communicate with broad-based broadcast communications that go back and forth across that environment. So we have to look at this from a different perspective, which is how is information transmitted and how does it flow across these hierarchical networks, ultimately to different servers or different centralized locations. So if we follow from the left side, we've got our different data producers. These are the same type of machines or applications or whatever data sources you want to talk about, that are generating information streams, and they're feeding that information streams into what you might call data collectors, whether they're servers that are sitting somewhere embedded within the network, or whether it's configured cloud-based systems that are instantiated on demand based on the volume of data. But you've got data that's being collected, then some kind of process that is ingesting and perhaps filtering and caching some of that data, storing some of that data, distributing some of that information to analysis applications. So whether you're looking at perhaps in some instances you're doing some operational activities, but in many cases you are feeding or forwarding the data that is flowing from these different devices into analysis applications that are looking to develop analytical models that can be used to help in making decisions automatically along the way. Some of that data is going to be persisted. Maybe it's filtered, it's reconfigured, it's transformed into format, it augments existing profiles, that type of thing. And at the same time, the results of some of that analysis, some of those analytical models are pushed back into different sites back within that network so that actions can be taken. So maybe back to a website, or back to a mobile device, or helping configure the types of offers that a customer service agent is giving you when you call in to complain about poor cable TV service, or your mobile phone is not working, your mobile phone service is not working the right way, to be able to help the customer service agent in some method of automating the recommendations for suggesting ways to improve the outcome of any of these situations. So whether you're talking about providing information to a live person, or whether you're talking about streaming information back to the devices from which the information was originated in the first place, that you might have some suggestions. For example, in a fleet of trucks, information is constantly being generated by each of the trucks in the fleet. Information about the traffic conditions along the different routes could then be forwarded into an analysis environment that would look at that across the different routes that those trucks are driving, determine whether they are on the optimal route for the particular conditions that are for which you've been made aware, and then perhaps reroute some of those trucks in the fleet to ensure that the deliveries are going to be made on time. Those are all examples of where you're collecting information from across the IoT network, and then being able to analyze the information and then push some decisioning recommendations back into the network. So that being said, what are some of the challenges of integrating and absorbing and processing and analyzing that data that originates across the different places in the network? And there are some key challenges that are associated with the scope, the scale, the variety, et cetera. Number one, I think this is one of the most challenging aspects of this, is the dynamic nature of the network. We're constantly adding new devices into our IoT network. We're constantly, we're at risk that there is going to be modifications to the ways that the data streams are being generated at each one of these devices, because you go out, you purchase a certain type of machine, you install that in your factory, and today it's generating data that in streams that has a particular sequence and a particular set of formats. And then the next day there's an automatic update to the interface, and there's a modification to the data stream, and there's a new attribute that's added. But there's no way of making sure that every consumer of the data that is being generated by that device is aware that that modification has taken place. Sometimes you need to have a means of raising awareness of those types of changes that happen within the network. So there's a lot of dynamicism in that network. Just the pure volume of the data. If you think about a truck that's driving down the highway with 100 embedded sensors, each one of them generating new readings every half a second. There's a lot of data that's being generated by purely within a single truck, and then think about having 100 or 200 or a fleet of 500 different trucks at the same time, trying to to ensure that you can balance the collection of all that information and forward it to the right kind of analytical environments. Therefore, there's a new question, or a new challenge, which is that need to ingest and filter and then subsequently integrate the data from those different networks, analyzing that data that's been ingested, and then taking the results of those analyses, creating analytical models that help with decision processes, and then embedding those analytical models at different points within your network. So I call that integrated analytics or embedded analytics. And this is a question that has come up actually in conversations a number of times that I've been involved with recently, which is the difference between analysis and analytics or embedded analytics. The question of analysis is where I'm collecting a lot of the information and I want to subject that to some kind of data mining or some kind of artificial intelligence or machine learning algorithms or some modeling algorithms that will generate some kind of artifact, some kind of analytical model that then is essentially some type of filtered / decision recommendation application that I can then embed within another device. So then that analytical model itself is looking at the data and triggering certain types of actions based on looking at the stream of information, comparing it to the current state of what's going on within its location within that environment. And so we're constantly generating data, we're constantly analyzing data, and we're creating these analytical models. Those analytical models are in turn need to be continuously tweaked based on the results of the recommendations that those models are presenting within the context of the business operations that are going on. So we have a little bit of a twinned challenge here, which is we need the data to do the analysis. We need the analysis to create the models. We need the models to help in the operations. When we help in the operations, we change the frame of the information that's being generated, which then has to be fed back into that cycle to improve the results of the analysis. We'll talk about that in a little bit, but I do want to talk about some of the objectives of building a data architecture that supports the IoT environment, or the IoT, I guess I would call it a framework or a paradigm, to be able to absorb information, to be able to make use of the data streams and the right context, and be able to get the optimal outcomes as a result of the analyses that you're performing. So objective number one, you need a data architecture that's able to adapt to the dynamic nature of the network topology. We're constantly adding new things into the network. The interfaces are subject to change without notice, so we want to have a data architecture that is flexible enough that it can easily be adapted as things change within the network. Number two, simplifying integration of those different, what we call, if we're talking about the Internet of Things, then we want to simplify the integration of those things, which says that as new data streams are coming in, we don't want to have to wait a long time to figure out what the stream means and what is being generated and how we can use that within our analyses. We want to make that simple. Subsequently, we want to facilitate agile development. We want, if we want to be reactive in a clever way or an informed way to changes in our network, we want to be able to make use of what we've learned and how to rapidly integrate those changed or modifications to that environment into our holistic or system for doing ingestion, analysis, and production of our analytical models. That says we have to be able to ingest streaming data, we have to be able to integrate streaming data, and we have to do that in a way that is thoughtful and knowledgeable about the context in which the data originates. And as a result, we want to be able to enable analytics, not just the analysis of what data comes in, but be able to take the outcomes, those analytical models, and be able to deploy those analytical models in the right places within the network. And then finally, we want to make sure that those things are doing what we want them to do. So we have to embed governance and some level of control in our network so that we can monitor what's going on and be able to identify when we're getting a level of improvement that we expect or beyond what we expect, or whether the level of improvement is missing our expectations as well. So let's talk a little bit about some of the aspects of that, of what we need to do in order to do that. The first thing is that we have to have a good understanding of the IoT data flow. I'm going to give an example of the evolution of an IoT network. The first is, think about a factory. Factories have a number of different assembly lines, you might say. On each one of those assembly lines, they have some different types of devices. They might be devices that are being managed by people. They might have some robotic devices. They might have some monitoring going on. Each one of those devices may be configured with collections of sensors and actuators, et cetera. So an example might be on that assembly line, you might have a air quality sensor, you might have a vibration sensor, you might have a heat sensor, and a combination of the data streams would provide you with the information that says maybe this machine is running too hot, we need to slow it down. Maybe there's the air quality is impacting the physical aspects of some of the hardware inside one of those the machines. So gears are getting gunked up and there might be a failure. So the idea is if we can collect information, we can monitor things for safety, monitor things for potential opportunities for maintenance, et cetera. So each one of those devices is going to be generating a bunch of data, and that data, all those data streams might be collected into a single server that's sitting on each floor of perhaps a factory. Well, if we can put that into a floor in the factory, then perhaps we might be putting, we have multiple floors in a single factory. And if we have multiple floors on the single factory, well, we should be connecting those servers that are associated with each floor and monitoring each one of those assembly lines into yet another server where I can collect information about what's going on at all times within all the different floors of that factory. And of course, what that means is that I might have multiple factories, so I might have the same kind of configuration going on at each one of my factories. So now all of a sudden, what was at one point just a collection of sensors and devices on particular machines on a single assembly line in a single factory now turns into a collection of sub-networks associated with all the different floors in all my different factories. And I might then want to stream all that data collected from all those things to some centralized server that's going to be monitoring the performance across all the different floors in all my different factories to build analytical models perhaps for what we call predictive maintenance. So if we have a bunch of the same types of machinery in each one of these factories, then we can monitor what happens at what point over time do we get part failures, and then are we able to look at predictive models that will say under these types of conditions during this type of operation over this period of time, we can anticipate that the following parts are going to need replacement within the next 2 days. Then you can schedule replacement of those parts instead of having a failure on one of your lines and shutting down an entire line in an unanticipated way for an unanticipated duration. So the ability to do predictive modeling for understanding predictive part replacement actually can save a lot of time. Well, what happens here is that we're not just streaming data from the different devices into that centralized server. We're actually going to take the results of those analyses and push them back out. So I don't want to have to pull all the data from all of the devices into the centralized server and then run my model at the centralized server to do predictive maintenance. I can push all those models back down to the different floors in the factory so that an analytical model is looking on each floor so that I can get the information faster and run those those filters or the analytics much closer to where the part might need to be replaced. So device data are streamed to a centralized computing environment. Analyses are performed and analytical models are created, and those analytical models can be deployed across that IoT network to automate that decision making. That's an example. So to be able to address the data architecture to achieve our objectives, here are some ideas. Number one, intelligent stream processing. So information is, you'd call that the lifeblood of the IoT environment, and you really think about it that way because information is flowing from the devices to the centralized environment and then back to those devices. So it really is a circulation system of information. To be able to make sure that works, you have to ensure that there's connectivity, that there's coherence, that the information that's being produced at the device is the same information that is being delivered to the different absorption points along the way. To look at synchronization of information, we don't want to be trying to analyze data that comes from one set of devices today with data that came from a different set of devices 2 months ago. We want to validate the data, make sure that there's no problems in the system that are introducing flaws into that environment, into the data streams. And then finally, integration. We want to be able to transform those different streams into some kind of standard representation that simplifies the way that we can collect that information and then forward it to our types of analytical environments. So that makes a suggestion for there being something that you might call intelligent stream processing that blends mechanisms for managing information streams or data streams like Kafka or Storm with map data flows, parallel processing, and data discovery, so that if you recall that we talked about the whole question of the variety and the dynamicism in the environments that creep in, that we have a mechanism for identifying when there are modifications to a data stream and that we need to alert the right people that modifications might need to be made. Now, if we do that, we have to understand the metadata and the information about that information, and do that also in a way that's intelligent. The question is, we've got a dynamic environment, so if we want to adapt to a dynamic environment that have data streams that are being forwarded to different analysis systems and integrated analytical models, we have to be aware of what that data stream looks like and when those data streams change. So if you are developing your applications that are sitting across that network, the application developers have to be aware of what are the data sources and what are the structures of the streams, and a little bit more importantly, what's the semantics associated with those data streams? What does it mean when I see certain types of values in certain types of fields, and what happens when there was a modification to that representation, and when a new attribute is added in, and what are the changes to the APIs? So you're pulling data from like a social media network, and there's a modification to the APIs. You have to be able to be aware of that as well. So this concept of a data catalog and a services registry allows you to keep track of data stream metadata and the mechanisms by which those data streams can be read and ingested and managed. That ultimately will simplify the development of those applications that are integrating those embedded analytical models. This concept of state needs to be thought about a little bit. Now, what do I mean by state? Well, I'll define it for our purposes as the temporal context of existing relevant knowledge upon which analytical decisions are predicated. So, for example, I gave the example earlier about monitoring the air quality and the vibrations and the temperature in a factory floor. Well, over time, I'm going to be looking at how there's the variance of those different variables. Maybe it gets hotter during certain times of the day. Maybe it cools down late at night when the machines are shut down. But I want to be able to understand that changes in the temperature at a particular location at a particular time of day have different meanings based on the context. So if I see that over time I anticipated that at 3 o'clock in the morning when the machines are supposed to be cooling down, I see an increase in the temperature along certain parts of assembly lines on one floor in a factory, I might want to alert somebody to that because that might mean that there's fire in the factory as opposed to an increase in the environment, the heat of the temperature of the environment because of all the machines running at the same time. Because it's not anticipated based on the history of activities and the readings that are coming from those different streams. But So what that means is that I have to keep track of what I call state, which is the last views of what's been going on for some particular time period. And analyzing streaming data has to encompass monitoring for changes in that contextual state, and the aspects of the context may increase or decrease in relevance over different time spans. So the relevance of the variables that I'm monitoring in my state erodes over time. So I need to have some concept of what you might call adaptive analytical modeling that allows you to use sliding windows for maintaining that state. So you can use those sliding windows to maintain local history, to do real-time analytics, and to monitor what's going on, when you expect it to be going on, and to abandon the need for monitoring certain types of state when the context is no longer relevant, without introducing artificial delays into the process. So this image here looks at context being framed in terms of sliding windows, and that when events take place, you do the analysis of the event based on the different frames of those different windows, and at certain points the context is no longer relevant, so I no longer need to keep track of information associated with what was going on in those earlier windows. So that's what we mean by adaptive analytical modeling, and I think there's some other aspects of that which I'm hoping Dinesh will share as well. Here's this other concept of pushing analytics to the edge. So analytical models don't have to reside solely at that centralized computing environment. We can actually push those models strategically to be embedded close to where those decisions need to be made. So we don't need to always be pushing all the information back at all times for all analytical models to be sitting in some centralized server. It's going to create number one, a bottleneck, because you're going to be waiting for all that information to cross your network, get analyzed, and then have the results sent back, as opposed to being able to, if I need to make a decision about shutting a particular machine down on a particular assembly line in a particular floor at a particular factory, I don't need to collect all the information from all of the machines, lines, floors, and factories to be able to make that decision. So that's the idea that eventually the ways that we're going to be doing our analyses are not just going to be the centralized analysis, creation of models, and push the models to the edge, but we may even be able to push up some of the analyses to different layers in this hierarchy and closer to the edge, so that we've got essentially like what you might call a fractal model of analysis, meaning that we have to have more streamlined mechanisms for doing data streaming, ingestion, and being more clever about how we architect our data flows so that we can take advantage of those opportunities. Oh, there we go. What I was saying is that we could push the decisioning to different locations within our network there. And then this other concept that we were talking about in terms of monitoring how good our analytical models are. So we want to combine our embedded analytics with integrated performance monitoring as well as reporting. So if we've got a analytical model that we've pushed to the edge that is helping in making decisions about operations in a particular location or within the context of a number of specific devices, we want to monitor how good those decisions are and then be able to take the results of that monitoring and push that back. So we can install monitoring at the edges along with those analytical models to log the decisions and the corresponding outcomes. Did we shut down a machine? If we shut down a machine, how did that impact production? How did that impact the other variables that we're monitoring, air quality, et cetera? We can use now. This becomes another streaming data source. Once we're creating these performance monitors that we're embedding within our network, it becomes yet another data source that we can stream back to our centralized server to provide a feedback loop for analytics performance. Well, it allows you to let machine learning algorithms monitor the performance, then tune the models. So you can tune the models based on what was going on as a result of the earlier instances of those models and improve the models over time, so we can get improved performance purely by embedding yet another data source within our IoT network. Those are some ideas for influencing the way that we architect the data and information flow. Here's some considerations. These can overall enhance the effectiveness and optimization of the behaviors of your different applications across your IoT networks. If you want to take these ideas and actually design your architecture and operationalize it, it depends on introducing technologies into that environment or the IoT paradigm that include things like data catalogs, services registries, a metadata repository, controls, integrated analytics, data flow modeling, data lineage modeling, embedded governance, and what you might call intelligent stream processing. So those are some of those ideas. And I want to share, or basically kind of share that back with and ask Dinesh to share a little bit about what Hortonworks is doing and how they're looking at solving some of these problems.
Yeah, thanks, David. Before I introduce Dinesh, just a quick reminder to the audience that we welcome your questions. I see some good ones coming in already. I know David looks forward to answering those as well as Dinesh, so type them in on your console, send them over, and we'll get to those after the next presentation. So on that note, please welcome Dinesh Chandrasekhar, who is Director of Product Marketing with Hortonworks. Dinesh is a technology evangelist, a thought leader, and a seasoned product marketer with over 23 years of industry experience. He has a track record of taking new integration, mobile, IoT, and big data products to market with a clear go-to-market strategy. Dinesh has extensive experience working on enterprise software as well as SaaS products, delivering sophisticated solutions for customers with complex architectures. As a Lean Six Sigma Green Belt, he's been the champion for digital transformation at companies like Software AG, CA Technologies, and IBM. So Dinesh, good to have you here. Let me turn things over to you.
Thank you so much, Linda. Appreciate it. So let me kick it off by saying Hortonworks has, as you know, is a 100% open source company. We've been around the block for like over 7-8 years now, and we started off originally as a Hadoop distribution kind of a company, but over the years we've been evolving our strategies, and today we are a global data management company that offers solutions across multiple different portfolios, including IoT. And today what I wanted to discuss is our vision and our point of view around IoT and how our customers are leveraging our solutions for solving some of the most complex IoT problems within their spaces. What I like to call about the use cases that our customers are addressing is this notion of data-driven IoT. So the notion of how IoT and data are like tied at the hip, and how some of these use cases are not going to be addressed if they are not going to be tackling the problem of how to harness the value of the data that from IoT. So let's look at the landscape here, right? I mean, this is kind of like pretty typical of the Hortonworks customers' landscape. We have customers across all different, industry verticals: development, manufacturing, distribution, marketing, sales, service, and beyond, right? And each and every one of those verticals, if you look at, some of the use cases there, or some of the products or the services being offered within those verticals, you see a connected pattern there. And the pattern is all around like the notion of connectedness and how each and everything is around IoT and data being like the primary driver behind each one of these. And these are all, again, fantastic use cases for digital transformation. You do supply chain in a certain way. You've been doing that for the last 20 years, and suddenly you start like understanding, hey, I can leverage, sensors across my supply chain to understand, how to optimize and streamline my operations. Or I could understand the movement of goods within my supply chain, using these kinds of sensors. Or maybe even understand, some of the temperature and humidity monitoring needs that my supply chain has. So any one of those, requirements could become a digital transformation initiative. And as I like to say, IoT is fundamentally a business initiative to begin with. Most of these IoT initiatives are hardly IT driven. They're begin off by saying, this is a business initiative. I need to go into a new customer territory. I need to tackle a new channel that I'm opening up, or I'm wanting to streamline my operations. Any one of these business initiatives would warrant the need for newer digital initiatives, and that would include IoT. So if you look at that, what it has driven us to is a point of connected ecosystems, right? The reason why I mentioned that is because, again, the notion of IoT and data kind of tied at the hip. If you consider connected cars, which is, again, an example beaten to death across all presentations, but I'll also use that because it's so easy to explain and so easy to connect with, and we all have like some form of electric car or a connected car, and these days autonomous cars have come about as well. So it's something that we all can relate to. An average connected car today generates like over 4 terabytes of data a day, right? So it's like massive, and these are data points that David mentioned earlier. There's a humongous amount of data being generated by IoT devices. There is excessive velocity at which these data is like hitting the enterprise, and there is a strong need to understand that and capture that in real time and make value out of that. So in this particular context, the data that is being generated from the connected vehicle is not just being leveraged by the car manufacturer alone. There are multiple ecosystems that are feeding off of this data. So you have DMV type of entities that are feeding off of this, or connected cars are leveraging DMV data. So there's a vice versa kind of a relationship. There is service. There are service teams, from the car manufacturer or from the car dealerships that are harvesting this data and understanding when to send out maintenance reminders, when to offer roadside assistance, or maybe some kind of discounts based on how they've been driving. So any one of these, become add-on monetizable services that they can offer based on the data that the connected car is generating. And another aspect is insurance. And this has become a big, huge industry where insurance companies are now able to tap into this connected car data, and they can assess how good of a driver you've been, how much of hard braking do you do, how much of fast acceleration do you do, whether you've been breaking speed limits. All these data points are collectible and reportable. I mean, I get a monthly report from my car that says here's how you've been driving this last 1 month. So this kind of data then goes into my insurance record that can then say, have you been a good driver? I can give you a 15% discount based on your driving record. Or, you've been a bad driver, I might have to bump up your premium based on the risk assessment that we have had. So any one of these scenarios, again, goes back to the notion of how IoT and data are tied at the hip. So if you look at that, then this is the fundamental premise of how you measure IoT success. Right? Your IoT success, your IoT implementation is only as good as your ability to acquire and analyze the real-time data generated by your IoT implementation. And let that sink in, because this is very important to understand. A lot of companies fail at their IoT implementation, thinking that, hey, I deployed a whole bunch of devices, but I haven't seen success come out of it, or I have had thousands of smart meters deployed, but I'm still not realizing the value of it or something. The value truly comes from how good you are able to harness and harvest the value of the data that is coming from those devices, and how quickly you're able to. And that's the whole point of it. So look at a scenario like this, right, where there are real-time data sources. We talked about connected supply chains. David talked about trucks and monitors and sensors within them. Those are all realistic examples. Today we have refrigerated trucks that are going from one end of the country to another end, delivering perishable goods like milk and dairy products and cheese and whatnot, or even pharmaceutical goods that have a need to maintain a specific temperature and humidity within the refrigerated trucks. And so there are sensors within that monitor that and understand how these particular devices or these particular products are being maintained. Early on, there used to be log data readers, that kind of kept a log of all the different temperature at various points, and then, the driver would assess, or the person that is receiving it on the other end, would assess the log data reader and would go through the log and figure out if the temperature fluctuated at any point or not, and if it did, if they lost all the goods based on how the temperature fluctuated. But the need for real-time data, comes there where you can fix the problem right then and there. If for some reason the truck, had a bad bump on the road, or maybe there was a terrible roadway that caused, the goods to shift inside and block certain air vents, increasing the temperature thereby. So any one of these scenarios can be fixed right then and there instead of having to wait like 2 or 3 days to discover that the temperature actually shot up inside the refrigerated truck. So this is a good example, right? So this is a need for real-time data source to be combined with enterprise transaction sources. And everybody is driving towards the data lake, and the data lake is good in certain cases, and it's not so good or doesn't complete the comprehensive solution in a lot of scenarios, like even, for example, IoT. There's scenarios where you need intelligence right then and there at the edge and all that. Then a data lake is partially the answer. There are needs for giving that kind of capability right at the edge itself. So in this context, you have a need to ingest the data. You have a need to store the data and process it, and then subsequently analyze it and learn from it. You can build machine learning models out of such data lakes, and eventually you are able to put that back into wherever it needs to, for example at the edge, and create that kind of monitoring and provide the right kind of insights thereby, right? So this is kind of a good example. What is a key takeaway from this is that there is data decay that is happening around us. And this is inherent within an IoT scenario because a piece of data is only valuable for a certain period of time. I mean, David talked about sliding time windows. This is kind of very close to that, where that particular data point is going to be valuable to you within that opportunity window. And if you don't use that, then you're going to miss it. So, for example, if the temperature fluctuation was caught right then and there, it's good for you. But if you don't capture it at that point, then you're going to be looking at spoiled goods 2 days later. So that's the kind of data decay we are talking about here, right? So if you understand that part, then the need for processing and analyzing the data and combining that with insights that you've already learned, machine learning models that you've already built, that can teach you saying, this is a pattern that I've already observed, and here's how you can quickly react to it. So it can tell you this temperature trend is not good for this particular product. We should take corrective action right away. Let's send out a notification to the appropriate people. So taking corrective action is going to be the key outcome of some of these scenarios where you can address data decay right then and there. And this is inherent and very, very important across multiple industries. Healthcare, patient experience, everybody's trying to do this, biometrics. We have customers like ClearSense that are already, doing it actively, connecting IoT devices, to patient monitoring health devices like BP monitors or blood sugar monitors and all that, and then connecting up into real life feeds and trying to correlate that with patterns and indicating to healthcare staff saying this particular patient requires immediate attention. So that is again a notion of how you can capture IoT data in real time and respond and take corrective action in real time. Predictive maintenance, customers like Renault are using this for on their manufacturing floor, where they can understand when a certain piece of equipment needs to be fixed or addressed and maintained or updated in a certain point in time to ensure smooth operations across their manufacturing without any kind of downtime. And you can apply the same thing towards utilities for outage monitoring or smart cities and so on and so forth, right? So there are a variety of different use cases across all these different industries where IoT and real-time data become very, very inherent. So how does Hortonworks enable that? We understand that modern data architecture is kind of inherent everywhere, right? So we have customers that have a combination of data at rest, which is all the data that you collect in your data lake, and you're trying to build out machine learning models and all that, where you provide this deep historical analysis, and also the prevalence of IoT and edge analytics and social mobile and all these types of ecosystem participants as well that add to the complexity of the data architecture. And, throw in multiple data centers and multiple clouds and all that. And today this modern data architecture lends itself to what is the reality across, enterprises today, right? Every enterprise that even is on the call today that is like listening in, all you guys can correlate or relate to this and say, yeah, I have a similar setup where I have all these different aspects or facets to my architecture. So to enable a modern data architecture, we have a connected data platform, and one of the key tenets of the connected data platform is Hortonworks Data Flow. Hortonworks Data Flow is the data in motion platform, which helps you with the data ingestion that we talked about, from IoT devices or any kind of streaming sources like click streams and web streams and social streams and whatnot. So you can pretty much ingest data from all these different sources as well as from IoT devices, transform them, route them to any kind of stream processing system or to a data lake. It's got over 260 plus, it's not correct, 260 plus processors that help you ingest and transform the data to various endpoints. It can support not only data collection within the enterprise or at the enterprise or at the different endpoints connected to the enterprise, but it can also go across to the edge as well and enable data collection at the edge using Minify agents. So so the entire flow management capability is supported or powered by Apache NiFi, again an open source solution. Scales up extremely well. We got fantastic use cases where we are talking about thousands of IoT devices or thousands of streams. We got a customer that is called Prescient. It's a travel risk assessment agent company, and they collect data from 49,000 sources. So it's a fantastic use case of how they collect data from all these different sources using NiFi. And then the stream processing angle is what David mentioned about technologies like Kafka and Storm and all that provide the ability to not only take the data from NiFi and those kinds of data flows, but ability to process them and understand and make pattern matching and create predictive analytics out of that. So that's the notion of stream processing. So that is something that is possible within Hortonworks Data Flow as well. So we take data all the way from the edge into the enterprise. So you can have Minify agents sitting at the edge collecting data from the edge. These are really small, nifty agents that can sit inside even IoT devices. And, it lends itself to an architecture where you can enable edge intelligence kind of scenarios as well, right? So you can collect data from the edge, push it through NiFi into your analytics cloud sitting inside your enterprise for predictive analytics and all that, and then push it back as well where appropriate. So this connected data platform is what Hortonworks offers. We talked about data flow. There is data at rest support as well, which is the core Hortonworks data platform, HDP. And together, we are able to look at it from a global data management standpoint using Hortonworks Data Plane Service, DPS, which offers the notion of unified security and governance and all that. So together, we can take historical insights and perishable insights and provide actionable intelligence for your IoT architectures. So with that, I will pause and throw it open for questions. So we can let Linda kind of look at the questions and let us know which ones to take.
All right, thanks, Dinesh. Yeah, let's move into the question and answer period and get some of these audience questions answered. I want to start with one to David, but of course, Dinesh, I welcome your thoughts as well. So someone is asking, on the IT side, configuring IoT is okay, but what needs to be done at the production lines? For example, in a manufacturing company so that we capture all kinds of information. Do we need to install sensors, at each production line on the production line floor so we capture everything? Is that correct?
In a sense, yes, that is correct. On the IT side, of course, we have the control, and that's basically the type of tools that Dinesh was talking about, is that we have control over managing the information environment from the point where the IoT devices are generating the data or where the sensors are generating the data. Now, that being said, that doesn't mean that you have to go and reconfigure your entire, let's say you're a manufacturing company. You don't have to go reconfigure your, every single device on every single floor. What it does mean is that you have to look at, because the reason I say that is that most of these machines and devices already have integrated sensors that are generating data. In fact, going back many years, a lot of these machines have different types of connectors that have the ability to stream information from the sensors that's already being done. The problem is that there was no standard set for how all the machines are doing this, which means that you've got RS-232 cables coming out of some machines, and you've got some machines that are projecting or broadcasting their data streams through Wi-Fi, and there's a kind of a mishmash of the data streams that exist there. So there are organizations or the companies that generate certain types, or they don't generate, they manufacture edge nodes that are certain types of computing devices that can harness a number of different streams that already exist from a number of different existing types of protocols or mechanisms for communication, and can then harmonize those data streams into ones that can be consumed by your centralized environment. So it's not. The answer is sort of. There may be some kind of installations or modifications to the machines that are on each production line, or whatever your IoT network looks like. But it's not a complete overhaul. It really is just a set of adaptations to much of what already exists. And then if you've got machines that are so old that there's no connectivity associated with it, then there are also companies that create devices that include sensors for different types of variables that you want to monitor as well. So there are ways of adapting your environment so that it can hook in directly into the information architecture.
May I add one more thing? So one of the things that I would like to always emphasize is, when you talk about IoT and you talk about need for a solution like this, should I add a sensor or not? Question, what use case it is, right? So it's a very important thing to ask. What is your use case? Why are you trying to add a sensor? For a manufacturing kind of a company, there are 2 or 3 use cases that I can suggest. For example, predictive maintenance, which I talked about earlier. One of our customers, Renault, is actually using IoT sensors on their manufacturing floor to understand predictive maintenance and let them know of when their machines need to go through maintenance based on how many different cycles a particular machine has gone through, or how many different widgets it has produced, or how much it has been in operation, calculating the time it has been on and off and all that, or the temperature at which it is performing, any one of those. So for each one of these use cases, within the predictive maintenance part itself, you might want to may use or may not use a sensor based on what your requirement is. If you're going to be saying, I need to change oil for a particular machine, then you want to understand oil level sensors maybe, or even if it's based on temperature that you want to cool it down and you add some kind of additive or coolant or something, then you might want to include a sensor based on that. So it depends on the use case. That's why I would say look at what your use case is and then make that corrective change accordingly. But yes, sensors definitely galore is what I'm seeing.
That's great. Let's go to a question about data lineage, and I'm going to hand this one to you first, Dinesh, and then maybe to David. So David talked about capturing and managing metadata associated with data sources and about managing data flow. The question is, what is the best way to capture the data lineage? Dinesh?
Yeah. No, it's a very important question because, we live in an age of, GDPR and other such, compliance regulations happening across the world. So every company is trying to understand, where did this data come from? Who sent it to us? How do I manage it? Who changed it? What point did it change? What was the original value? What is the current value? What were the delta points? So this is a constant ongoing thing for auditability and compliance reasons. And people often look at their data lakes and or their existing EDW scenarios, and they go like, yeah, I need to understand data lineage at that point. But what they fail to do is an IoT scenario, which is even more complex because you need to now track all the way from the edge to the enterprise. So it's even more important for you to understand where the point of origination is, what the data originally was, and then track it through all the way to the enterprise, maybe to a data lake, and see, what the different changes or transformations the data has had. And so it's not straightforward, right? It's not easy to do something like that. However, with a tool like Apache NiFi, it's inherent within that. Apache NiFi supports something like this. And then, you throw an Apache Atlas on top of that. Then you have, Apache NiFi supporting edge to, enterprise kind of data lineage. It tracks complete change of the data tracking all the way from the edge to the enterprise. And then Atlas, kind of monitors, across multiple data sources and maintains the data provenance for you across, all these different data sources as well. So whether on premises or on the cloud or within a data lake or, within a data warehouse, doesn't matter. So that can help you as well. So that's how you need to look at it. And it's a very important topic for anybody that is considering IoT to pay attention to data lineage and provenance as well.
Okay, let me go to another one for Dinesh. How do we leverage the analysis code already written in a traditional data warehouse? Can we some way reuse that in HDP to remove some development effort for analytics? Dinesh, can you take that?
Sure. So there are multiple ways of looking at it, right? Let me see if we leverage the. It's written in traditional. And then can we some way? I'm just reading the question here. Sorry.
Sure, no problem.
So the question is kind of a little confusing. I cannot quite clearly address that right away. But what I can say is that it depends on what the code is written in, right? So first off, the question is a little unclear. How do we leverage the analysis code written already? So what is it written in, and then understanding how we can reusing that in HTTP again is also a little confusing because HTTP is a data lake, or you can look at it as a data lake or a data platform, and so looking at the analysis code inside HTTP is a little. So maybe I should just punt the question. I apologize. It's not a straightforward question, and it's a little confusing to. There are too many open-ended ones here. I apologize.
Yeah, no problem at all. I can send this one to you afterward, and you can follow up in a little more detail on that. Yeah. We're actually out of time here, so I think I'm going to go ahead and wrap up. I want to thank our speakers today, Dinesh Chandrasekhar with Hortonworks, joining our own David Lotion with Knowledge Integrity. Also, thank you again to Hortonworks for sponsoring today's webinar. We always appreciate that. I want to remind everyone that we did record the event, and we'll be emailing each of you a link to an archived version of the presentation. Please feel free to pass that link along to colleagues. And finally, I want to remind you that TDWI offers a wealth of information, including the latest research reports, webinars, and information on business intelligence, data warehousing, and a host of related topics. I encourage you to tap into all of that expertise. It's at tdwi.org. And on that note, from all of us here today, thank you very much for attending. This concludes today's event.